Hello everyone, my name is Olamide Confadonsi and I'll be presenting Edge scheduling framework for real-time and non-real-time tasks. I'm a PhD candidate in computer science at McGill University, and my research interests include resource management, scheduling in edge computing systems, Internet of Things, and artificial intelligence applications. My fellow authors are Yuzang Ma and Professor Mutkumaru Maheswaran. Yuzang is an undergraduate student at McGill. His research interests include edge computing and heterogeneous computing. Professor Maheswaran research interests include security, resource management, programming frameworks for cloud of things. So before I delve, I'd like to give a motivation for edge computing. So edge computing, currently we have five fast 5G networks, the Elastic Cloud, Power edge servers. This enables running old applications such as media streaming and messaging. But more importantly, we can develop new applications using this, such as real-time applications. So an example of a real-time application is a real-time AI application that is used to capture data at large rates and process them to extract intelligence, then access them in real time. Now, for our problem, I'd like to give a motivating scenario first. So what we looked at is we looked at applications such as collaborative robots, which are also called cobots. So what are cobots? So cobots are robots that deal with machines that heavily collaborate with humans in factory floors. They're expected to play increasingly prominent role in many other domains, for example, healthcare facilities. So their roles that were identified include automatic navigation on the factory floor, so they could be kept in a zone and where you have um, a lot of cobots mingling in that zone trying to carry out a task. So they navigate the factory floor. Then they also collaborate with other cobots and they can collaborate interactively with humans. And there's automatic monitoring of the cobots' out properties. So we identified three problems in trying to um, get these roles done. So we know that there are real-time deadline required for tasks associated with autonomous navigation. So without you completing the navigation process first, the cobots cannot carry out the next move, which brings us to the first problem, which is real-time scheduling and coordinated task scheduling. Now, another key purpose of cobots is collaboration with humans. So cobots can receive a lot of user interactive tasks, which, unlike real-time tasks, they can happen at human speeds and they can also tolerate low rates of error. So for users to have responsive interaction with cobots, they need to complete as many interactive tasks as possible before the sub deadlines elapse, which brings us to the second problem, responsive scheduling of interactive tasks. Then lastly, cobots need to run periodic health checks, analytics, and other data-intensive tasks to detect impending failures and keep the overall reliability levels high. So before cobots can undertake safety critical tasks, we need to schedule all the health checks to minimize cobot failures, which brings us to the third problem, high throughput batch task processing. Now, there's a common thing with all these things is we need an efficient resource manager to schedule and manage all the resources and schedule all the tasks, different tasks that makes the cobot function properly. So the resource manager needs to give an higher preference, right, to the real-time tasks, those that have deadlines, which are coming to later, and interactive tasks. However, if the batch tasks keep piling up, the cobot might have to be taken to a service mode so that the pending task can be cleared. So the resource manager needs to also shift the task scheduling preferences to cater to the changing requirements between the real-time task in P1 and the interactive task in P2. Now, what we're trying to achieve, what we're trying to do. So we're trying to schedule different task types using the edge computing architecture. We classify our tasks into three: batch tasks, interactive tasks, and real-time tasks in our work. So what are batch tasks? Batch tasks are tasks that have no deadlines. Interactive tasks are tasks that have soft deadlines. while real-time tasks are tasks that have deadlines and need to be completed within a given latency. So another assumption we make, a key assumption is that real-time tasks are periodic, while batch and tasks are aperiodic. So we developed a two-stage approach to efficiently schedule the task by guaranteeing the real-time task without constraints and maximizing the throughput of the other task types, which is the batch and interactive. So we propose a two-stage scheduling architecture. What it does is it maps tasks across a collection of edge computing resources. We call the first stage L1, and that does the tasks to resource matching while taking the task requirements into consideration. And it produces the schedules for the tasks, which is what you see in those purple boxes. The second stage executes the tasks on the resource while respecting the real-time deadlines of the task, and the non-real-time tasks are scheduled to use available free time slots. So using the image given is you have the cobots giving their real-time tasks to. So first of all, the cobots are in zones, right? And we have an edge zone manager and edge resources in that zone. So they send their real-time tasks to the edge zone manager. So what that does is after sending the resource, the task rather, they tell the edge zone manager what resources or what the resource requirement should be. I'll delve into this in the next slide. So what the zone manager does is it does the L1 stage scheduling, where it schedules the real-time tasks, and in the L0, it sends that schedule to the L0, which runs in the appropriate edge server, and the edge server executes the real-time task according to the schedule that it got from L1. And the L1, as I said, does the task to resource matching while taking the task requirements into consideration and generates the schedules for the tasks on the matched resources. So in the L1 stage, we run two algorithms in the exo manager. The first one is the task matching algorithm, and the second one is the scheduling algorithm. So for the task matching algorithm, what it does is you're given a set of tasks and requirements along with the resources. That's the task requirement. So I want to run on the resource that has this processing capability or that is on this location and so forth. So what the algorithm does is it matches the resources to the task based on the requirement, and it creates a feasible set of tasks for each of the resources. So using the figure I have there is you have the task being R1, R2, R3, and the resources being A1, A2, A3. So R1 tells you, okay, I want to run on all the resources. R2 tells you I want to run on just A1 and A2, and R3 tells you I want to run on A2 and A3. So the resources, so the task matching algorithm computes the priority values for that, and the resources match. They are matched to the task based on the priority values. Another thing we do is we now, after matching them, we now create a schedule for the real-time task by applying the scheduling algorithm, which I'll delve to in the next slide. But then we also compute Slack servers. So Slack servers are the idle processing time. So you schedule the real-time tasks and you compute the Slack servers for them. So in the scheduling algorithm, we take the set of real-time tasks from the task matching algorithm and we create an offline schedule. Now, two scheduling functions are included, which is the normal scheduling and the greedy scheduling. Now, you can call it normal mode and the greedy mode. So what the normal scheduling is just a representation of the non-preemptive earliest deadline first algorithm. The earliest deadline first algorithm schedules tasks based on the deadline as early as possible, while using their early time rather, while the grading scheduling function is a modified adaptation of the EDF using both earliest and latest starting time. Now, the two schedules, they give different distributions of the Slack servers. As I said, the Slack servers are the idle times that you have. So the difference being that in the grid schedule, processing time is borrowed by scheduling some task instances as late as possible, whereas in the normal, you don't borrow processing time, you just schedule them as early as possible. So there's an example on the left figure where we have a set of real-time tasks, and we have the normal schedule, and we have the greedy schedule. So I have the Slack servers and the pictures as S. So you can see the different distributions of the Slack servers. So those Slack servers will be used to execute the non-real-time tasks in the L0 stage. That's the second stage. Now, the second stage of our approach is given the schedule generated from L1, you submit it to the L0 scheduler running in the Edge server itself. So what the L0 stage does is you execute. So in the L1 stage, you schedule the real-time task. In the L0 stage, you execute those tasks using the schedule you've been given, right? And you now use the Slack servers to execute the batch and the interactive tasks. So, but to do this, you need a first selection, right? So we propose the first selection algorithm to help us avoid starvation of any of the task type, that is either batch or interactive, by introducing the concept of a virtual clock. So what we do is we select tasks whose virtual clock is lower anytime there's a Slack server available to serve a task. So the batch queue tasks, since they have no deadlines, they are sorted on FIFO, first in, first out, while the interactive tasks, they're put on the queue, which is sorted on their earliest deadline, since they have soft deadlines. So every time a task is selected, you want to run it on the Slack server, we increase the virtual clock by a function of the execution time of that task. So this way, we kind of avoid starvation between the two task types. So we select between the normal and the greedy schedules based on the fitness of the Slack servers. So remember, we're giving two schedules on the L1. So the fitness of the Slack servers means how the Slack server is utilized by the batch and interactive tasks. So adopting the best schedule between the greedy and normal schedule is also done in the L0 stage. For our results, we carried some sort of experiments, a couple of experiments, but we broke the results down into the two stages. The L1 stage with the task matching, and the L0 stage which executes the tasks. So in the L1 stage, we looked at something called soul matching and group matching. So soul matching is the edge servers arrive individually and are matched to the workload. Whereas in grouped, the edge servers are grouped and the matching algorithm tries to find the best way of satisfying the task requirements given the edge server capabilities. So for our experiment, we injected a workload of 7 real-time tasks to the L1 stage um, that has 4 edge servers, and the L1 stage matches the real-time task to the edge servers, and the L0 stage running in those edge servers get the actual task instances for the real-time interactive and batch tasks. So the batch and interactive tasks arrive according to a person process with the specified arrival rates that you see in the figures. So the left figure shows something we call the BI, which is batch interactive output. So the BI output is the number of interactive tasks completed plus the throughput obtained for the batch task. Remember that the interactive tasks have some deadlines, while the batch tasks have no deadlines. So we notice that the group have higher locality of mapping the task to edge servers, which explains the better performance obtained by the grouped matching. Another interesting observation that we notice is that the good proof for interactive tasks, the number of tasks completed before the deadline, drops as the arrival rate increases. This is because higher arrival rate introduces execution delays and make interactive tasks miss their deadlines. This problem does not arise with batch tasks. Now, once a particular LO schedule is matched on edge server, the real-time task instances arrive at the local scheduler in that server. So the throughput obtained is shown in the right figure. We can observe that soul matching outperforms grouped in terms of real-time throughput because the soul matches an edge server with columns in the task matching matrix, the ones with the highest priorities, because these columns have more tasks. So for the L0 stage, we focus on the performance delivered by that stage to the interactive tasks. We use a measure called guarantee ratio, which is the total number of tasks completed over the total number of interactive tasks that arrive to investigate the performance. So the L1 stage, as we said, provides the normal and the greedy schedules to the L0 stage. So we examine the performance of these schedules and an hybrid scheme that L0 stage implements, where it selects the best schedule between the two, that's between the normal and the greedy, based on the BI tasks mixed at the edge server. So this hybrid scheme is shown as the combined scheme in our figures. So in the hybrid scheme, the LO stage selects the best between the greedy and normal schedule by measuring the sum of work that can be completed using the two different schedules. For interactive tasks, the contribution to the measure of work depends on whether the task was executed before the deadline or not. So the hybrid scheduler assumes that the task arrivals have some local change, that is, the arrival pattern in the scheduling cycle is related to the pattern in the previous cycles. Therefore, the hybrid scheduler evaluates the schedule in a cycle or set of cycles and selects the winning schedule to deploy for the next few cycles. So the results show that the combined scheme is better than the normal or graded scheme in terms of the guarantee ratio obtained by the interactive tasks. So in our figures, we vary the arrival rates while the processor utilization due to the real-time tasks vary. On the left is 30%. You have real-time task utilization being 30%, and on the right, you have the real-time task utilization being 75%. So in conclusion, we highlighted the challenges involved with scheduling edge intelligence applications or AI applications by identifying three problems. We present a two-stage system model to tackle these problems. So in our work, applications have three types of tasks or three classes, which are real-time, interactive, and batch. The first stage matches the task to the edge servers by taking the execution requirements into consideration. It also provides two possible schedules, which we term gradient and normal to the second stage. Then it places Slack servers in the schedules that can be used by second stage to execute the non-real-time tasks. The second stage is responsible for adopting the best schedule between the two choices, that's the gradient and the normal, and that it gets from the first stage. So our results show that the flexibility offered to the second stage by the first stage, it allows them to meet the real-time constraints while maximizing the batch interactive task execution rates or deadline compliance rates. So if you have any question, I'll be glad to respond in the chat box. Thanks for listening.